These videos are to show the dynamic behavior of the normal eye using control theory. This leads to a predictive mathematical model for the normal eye's behavior. Now, ancillary to this, I must present control systems. Control system starts from a visual environment, which is decoded by the accommodation servo. An offset is applied of about 2 diopters. And the result is that you have an active control system that controls the refractive state of the normal eye. Now, strictly speaking, with respect to control systems, if you get 360 degrees phase shift, you get amplification, and the entire system will oscillate. The eye doesn't do this, but it's necessary to understand that that is a characteristic of a control system. So I will show this briefly. Here's a circuit consisting of an error detector and a motor, where the output of the error detector goes into the motor. The output will be shown on the meter, which becomes growing oscillations. And the oscilloscope will show the output of the error detector. All capacitors are the same, and all resistors are 47K. Here is the error detector when power is applied. Notice very slight variations. And 2 volt per scale. And because of positive feedback, we get growing oscillation. The same thing is seen on this meter. As the signal oscillates around 0. And this is the output of the circuit. Think of the motor oscillating back and forth under control of a very weak signal. Eventually the signal hits the stops, going from absolute max to absolute minimum. This is runaway oscillation for a control system. Here's the error signal on the 5 volt scale. Max to max. The system is a disaster. So that is what designers attempt to avoid. And they avoid it by mathematical modeling, or by actually building an analog computer of the system they want to build. You pick this up before you actually have this problem. A great deal of time, effort, and money and analysis is done to prevent this from ever happening. Thank you for your interest.